Hi Year 11, so this is your paper 4, so your written paper, and the physics questions start at question number 3, so if you turn there first and check if you need to go through any of those. So the first question for physics says an athletics race is started using a starting pistol. The sound from the starting pistol passes through the air, reaches the ears of the athletes. Sound waves pass the air as a series of compressions and rarefactions. Describe a difference between them. So you could have said two things. You could have said a compression has molecules close together, and a rarefaction has them further apart. I'm not going to be able to fit both in, sorry, hang on. Okay, so that's one option that you could have said. And then the other thing that you could have said is a compression is an area of high pressure, whereas a rarefaction is an area of low pressure. Obviously you don't need to say both of those things for the mark, it's just that either of these options would get you 1. Excuse me. So then an athlete in part B in the race has a mass of 70 kilograms. Her acceleration is 1.6 meters per second squared. Calculate the force needed to give this acceleration. So F equals ma, hopefully you remembered, and that's 70 multiplied by 1.6. And when I do that, I get a value of 112 newtons as the force required there. So then in part II, it says that the athlete reaches a maximum speed of 8 meters per second. Calculate the kinetic energy when moving at this speed. So again, you need to remember the kinetic energy equation, which is a half mv squared. It's the same athlete, so the mass is the same as before, so that's 70, and the speed is now 8 meters per second, but we need to square that. When I put that into a calculator, I'm going to get 2,240 joules as my answer for the kinetic energy. Then the last bit on this page asks you to explain the difference between speed and velocity. Okay, so speed is scalar and only has a magnitude, whereas velocity is a vector and also has a direction. Okay, so it's about referencing the fact that there is no direction associated with speed. In part C, it says the athlete is sweating at the end of the race and that the sweat evaporates off the athlete's face on a hot day, and to suggest why this happens. So evaporation is where a liquid molecule has enough energy to escape as a gas, and so obviously on a hot day more of those molecules will have enough energy to escape. So you just need to say more molecules have high enough kinetic energy to leave the liquid. As a gas. And then it says, name another way that the rate of evaporation can be increased. So we can have more wind to move the gas away from the area, so leave more space for that. Or also you could increase the surface area of the liquid. Don't give both options, you only need to give one, but I'm just showing you what the possibilities were. At the end of a long race, athletes are wrapped in a shiny foil blanket to reduce thermal energy losses. Explain why this helps to reduce that energy loss. So, you know that shiny things are good reflectors, but bad radiators. So, you want to say that the shiny foil will reflect the heat given off by the athlete back to them. Okay, so it traps that heat. So you could have said it traps a heat layer around the body. You could also say that air is a good insulator. That would be something else you could add as well. So 1 mark for referencing the fact that something shiny will reflect, and then 1 mark for saying that this traps a heated layer of air around the body. 2nd mark. Or you could have said for that 2nd mark that air is a good insulator. On the next question, which is number 6 for physics, the volume of the sun is given and the density is given, and you just need to calculate the density. So obviously to be able to do that, you just need to remember the density equation. So density is mass divided by volume. If I rearrange that, mass is equal to density multiplied by volume. My density given is 1410, and my volume is 1.4 multiplied by 10 to the 27, and when I put that into my calculator I get a value of 1.974 times 10 to the 30 kilograms. But if you look, this was only given to 2 significant figures, so really I only need to give this to 2 significant figures. Okay, so I can say 2.0 when I round times 10 to the 30 kilograms. So that's how I've got from here to here. Okay. Then it asks you to explain why the sun transfers energy to the earth mainly by radiation and not by conduction or convection. And that is because most space between the sun and earth is a vacuum. And we know that conduction and convection cannot occur in a vacuum. Okay. Excuse me, sorry, coughing away here. The sun emits gamma radiation and visible light. Both of these radiations are part of the electromagnetic spectrum. Place them into the correct part of the spectrum. So we know that visible light is right in the middle of the spectrum, so that's going to go there. Okay, it's in between infrared and ultraviolet. That one's fairly easy to remember. Gamma radiation is the shortest wavelength and the highest energy. Radio waves, on the other hand, have the longest wavelength and the lowest energy, so it's the opposite to radio waves. Gamma goes here. Okay, and then this one, just out of interest, would be, you don't need to add these in, but just to remind you in case it's helpful for the real exam, X-rays are the next energetic, then ultraviolet. Think about the fact that ultraviolet light is what gives us sunburn. Okay, it's a bit higher energy than the visible light. It'll help you to remember the order. And then microwaves is what's missing at this end. It's good to remember this order here, but you only needed these two to get the mark. So state why both these radiations take the same time to travel from the sun to the earth. Okay, they both travel at the same speed. It's as simple as that. and the value of that speed is 3 times 10 to the 8 meters per second. Alright, part D is still talking about the sun, and it's talking about visible light can be reflected, refracted and diffracted. You have to describe what happens when each of these things occur. So you just basically need to define what these things mean. So here we go. Reflection is a change in direction of a wave, okay, when they travel back from a boundary or a barrier. Okay, so we have a boundary here, we have the ray coming in, it bounces back into the same media that it was in before. Refraction is still a change in direction of a wave, but this time it's when it moves into another medium as it enters a new medium. So that's the material that it's travelling in. And then diffraction, again, is a change in direction of the wave. But this time it's as it either passes through a gap or around a barrier. Okay, that should really be or around a barrier. I should really add the word around there, shouldn't I? So they're all changes in direction of a wave, but the reason for that occurring is slightly different, and you just have to make sure that you've got all of those in there. Okay, the next physics question is number 9. So let's have a little look there. So we've got a radioactive source decaying by the emission of alpha particles. Now remember that an alpha particle is a helium nucleus which has 2 protons and 2 neutrons. Before we even get to the rest of the question, we know that they're used to destroy cancer cells. They are directly injected into the site of the cancer. Explain why it's only affected if we inject it directly. Okay, so we can't just have the source nearby and hope it will work. We have to think about why it is that we have to exactly add that in. We know that alpha particles have very low penetration. Okay, so alpha have very low penetration ability. Okay, and so we need to pop it in there so that it can get to the cancerous cells. If it's outside, it's not going to get into the cancer cells. Then we've got the source. What is the source? Astatine. Interesting. Decays by alpha particle emission to produce an isotope of bismuth. Use nuclide notation to complete a simple equation for the decay process. So we know that it is alpha decay, so we're going to have the helium nucleus for 2. It would be okay, I think, if you wrote the alpha symbol instead of He as well. I'd give you the mark for that. And we know that we have to conserve our numbers, so we have to have this number plus 4 equals 211, and this number plus 2 must equal 85. So we've got 83 here, and we've got 207 here. We just need to make sure that these add up. So you can see 207 plus 4 gives me 211, 83 plus 2 gives me 85. Okay, next bit. X-rays and ultrasound waves are used by doctors in hospitals. X-rays are transverse, ultrasound waves are longitudinal. Describe the difference between the two. So we know that transverse oscillations are at 90 degrees to the direction of wave travel, whereas longitudinal, sorry, I don't know what's going on with my brain today, oscillations are parallel to the direction of wave travel. Okay, so if we have a transverse wave going from left to right, the particles in its way will oscillate backwards and forwards at 90 degrees, whereas with a longitudinal wave, any particles in the wave will oscillate left to right, parallel with it. X-rays have a wavelength of 1.1 times 10 to the minus 9 meters and travel at obviously the speed of all waves in the electromagnetic spectrum. Calculate the frequency. So this requires you to remember the wave speed equation. So we have V equals F lambda, speed of the wave, is equal to the frequency multiplied by the wavelength. I can rearrange. F is V over lambda, and the speed is C, it's 3 times 10 to the 8, and the wavelength is 1.1 times 10 to the minus 9, and that gives me a frequency of 2.7272 times 10 to the 17 hertz, and then we're just going to give that to two significant figures, 2.7 times 10 to the 17 hertz. Okay. Ultrasound on the next bit, used to scan unborn babies. We can't hear ultrasound waves because the frequency is too high. Use your knowledge of the range of audible frequencies to suggest a frequency for ultrasound waves. So any number you give that is larger than 20,000 would be acceptable, because that's the upper limit of the hearing range. Okay, so you could say 25,000 hertz, you could say 30,000 hertz, anything greater would be fine. And so you're just saying that the reason for your choice is that it has to be greater, because that is the upper range for your hearing limit. Okay. Suggest why it's not safe to scan unborn babies with X-rays, because X-rays are ionising, and obviously babies are developing, and that can cause a lot of cell damage. Okay. Number 12 is the next one. Motion again, so we've got a speed time graph. You know that the gradient of this graph is acceleration, because it's speed, change in speed divided by time, y over x, and that is acceleration. So it asks you to calculate the acceleration of the train at 5 seconds. So let's have a little look. Let me zoom out so you can see everything. We can hopefully see that in the first section of the graph we have a constant gradient. That's a straight line according to my ruler. So 1, 2, 3, 4, 5, that's 10. So 5 seconds is obviously in the middle, that's there. So the gradient of this section is the acceleration at time is 5. Okay, so hopefully you can see that this section ends at 10 seconds. So we can use the change in y over the change in x over that point. So I'm just going to draw a straight line down here, and I'm going to use that whole triangle in order to calculate. So my gradient, which is my change in y over my change in x, I'm now going to read off this value of the top speed here, and you can hopefully see that we've got 16, 17, 18. That's 18 there. So I've got 18 minus 0 as my total change in speed across the 10 seconds. And my change in time that I've measured that across is 10 seconds. Is 18 over 10 is 1.8 meters per second squared. Sorry, I haven't even shown you that. There you go, so you can see what I've done. So just make sure that you're happy with how you've got that gradient. Then the train that it's talking about, we move on to an electricity section, has two large headlamps connected in parallel. They have a power rating of 360 watts and are operated with a voltage of 80 volts. Show that the resistance of each lamp is 18 ohms. So we know that power is equal to current multiplied by voltage. Okay, and we also know that V equals IR. Okay, so I've got a couple of ways that I can calculate this. So what I'm firstly going to work out is my current. So I is equal to P over V. The power of each lamp is 360. And the voltage across each lamp, because they're in parallel, they're going to get the same share. They're going to get 80 volts each. Okay, and when I do that, I get a value of 4.5 amps. Okay, now R is the voltage over the current. Okay. So now I know that the voltage across one of the lamps is 80, and I know that the current through one of the lamps is 4.5. Okay, and I get a value there for my resistance. But I need to show that the resistance of each lamp is 18 ohms. And in order to do that, I need to look at the parallel arrangement. Okay, so I'm going to sketch as well. Sorry, busy pausing my video here. I've unpaused. I'm not going to sketch just yet. I'm going to sketch on the next page. You can see when I plug 80 over 4.5 into the calculator, I get 17.77, which is approximately equal to 18 ohms. So that's enough for this section. It's on the next. I cut that bit, sorry. I am having a shocker here. I cut that bit of the question. There were too many marks. We don't need to worry about that. Carry on. You've shown that it's 18 ohms. 12C is looking at forces and resultant forces. We can see P, Q, R and S. Compare the sizes of Q and S when the aircraft is accelerating. Okay, so we know that the aircraft is accelerating in this direction, and we know that A equals F over M. So for the mass of this plane, we need a resultant force in order to have an acceleration. So one of these forces has to be bigger than the other for there to be a resultant force in that direction. Okay, so we are going to say that Q needs to be bigger than S. So that there is a resultant force. Okay, so Q is bigger than S is the most important thing. State which is the weight. Well, that's quite clearly the one that's acting down towards the centre of the Earth. So that's R. That shouldn't be too difficult. And then it asks you to complete the sentence to describe the relationship between the mass and the weight of an object. And so here you just need to say weight is the effect of a gravitational field on a mass. I think this might be the last bit. Okay, so we've got a speed time graph here. too big to fit, sorry. So, because it's a speed time graph, the gradient is acceleration. Calculate the acceleration between 5 and 45 seconds. Show your working. State the units of your answer. So units are important here. So we need to look at the acceleration between 5, which is at this point, and 45, which is at this point. And it's quite clearly going to be the gradient, so it's going to be the change in y over the change in x. So I'm going to draw my triangle on. Like this. So change in y over change in x. It's going from 55 down to a value of 5. And that is occurring from 5 to 45 seconds. So the difference there gives me 50 over 40. Okay. And I'm going to get a value of 1.25 meters per second squared. It is important to get that unit right there. So that should all have gone down at the bottom, but your acceleration is 1.25 meters per second squared. You could also have written that as ms minus 2. That would be fine as well. Oh no, one more page. Okay, state the two types of energy gained as the aircraft continues to accelerate and gain height after takeoff. Alright, if it accelerates, it speeds up. So V increases. Kinetic energy is a half mv squared. So if V has gone up, then kinetic energy has also gone up. If it gains height, GPE, gravitational potential energy, is mgh. H is increasing, so GPE also goes up. So the two types here are going to be kinetic energy and also gravitational potential. Write it out in full, don't just put the symbols there. Last but not least, you've got a gardener randomly using a leaf blower. You've got the energy inputs and outputs, and you have to work out the efficiency of the leaf blower as a percentage. Okay, so we have to look at the widths, so we can use the number of squares to help us work this out. Efficiency, firstly, is useful energy output over the total input, and to get that as a percentage, I then multiply it by 100. So the total energy in is 1, 2, 3, 4, 5, 6, 7, 8 squares, so we're just going to call that 8. Okay. The useful energy output is 1, 2, 3. And then obviously 1, 2, 3, 4, 5 is wasted because 5 and 3 make 8. Okay, so I can do 3 as my useful energy over 8 multiplied by 100. And you will get an efficiency of 37.5%. There you go.